Hey there, Mr. Wigglesworth. Are we going to get you some lunchy? Oh, sorry. Hi! There, I'm Star Scientist Bob, and this is Fun with Science. Today we're going to learn about refraction and its spectacular properties. First off, let's explain what refraction is. Refraction is the bending of light as it travels through different mediums. The denser the medium is, the slower the light travels through it. This change of speed changes the direction of the light wave, but the frequency of light never changes. Therefore, the dependency of wavelength manipulates light waves to separate. This is how it works. The light source creates an incident ray which penetrates through a new medium and is measured at an angle of incidence from the normal. An imaginary line that is perpendicular to the boundary is shown here. Well, the incident ray becomes the refracted ray as it bends towards normal. Here are a few vocabulary words we'll need to know throughout. The index of refraction is the measure of the bending of light when passing through one medium to another. Optical density is the ability of an object to absorb light. Dispersion is the distribution of objects over a wide area. A great way to look at this is through a prism. Is there a fly in here? When shining light through a prism, the non-parallel sides help with the separation of visible light into colors. Each color is a characteristic of a different wave frequency and wavelengths. Red is refracted at the steepest angle, around 42 degrees, then orange and yellow, etc., until it reaches violet, which refracts the least of the colors at 40 degrees. There isn't a big difference in bending, but the effects are phenomenal. It is truly amazing. Now that we have a fine understanding of dispersion, let's jump into more detail. We know that once the incident ray penetrates through a new medium, it changes direction and is referred to as the refracted ray. But what if the refracted ray doesn't exist? How can that be? Well, the angle of refraction depends on the angle of incidence, so sometimes the angle of refraction is not created. The angle of refraction can become so big that it is perpendicular to normal. This is called the critical angle. If the angle of reflection is greater than this critical angle, there is no refracted ray as a result. This phenomenon is called the total internal reflection. It can only occur when light travels through a medium to meet another medium with a lower index of refraction. This here is an example of total internal reflection. A laser beam is shot through the side of a fish tank and travels through the water contained inside. At the surface of the water, the critical angle is exceeded, so the ray does not refract. Instead, the surface acts as a mirror and reflects the ray. I know we're all having a grand old time, but let's jump to a message from our sponsors.
What you doing, Richard?
Oh, hey Jenny. I'm just trying out my new Periscope.
Oh, cool. What you doing with it?
Well, I can't see over this wall, so this Periscope will help me. It works by manipulating the path of light with mirrors on the inside. The mirrors are placed 45 degrees of each other, which reflects the light by internal reflection and allows us to see over or around obstacles.
And that little thing? Oh boy, can I try?
Sure, Jenny.
Wow!
Hi there, and welcome back to Fun with Science. Let's talk about another refraction phenomenon known as fiber optics. Fiber optics are tiny flexible tubes of glass known as optical fibers and are used to conduct and transmit light. The light inside is transmitted by total internal reflection, as we learned about before the break. Fiber optics are very useful with our everyday lives by supplying us with TV or telephone signals. Because the fibers can be very long and allow multiple signals to carry through it at one particular moment, it is more practical than the conventional metal wires. Let's transition away from these basics and start talking about my favorite refraction phenomenon. Do you ever wonder why on a hot summer day there seems to be a mirror-like surface 100 yards ahead of you? This cool trick on our eyes is called a mirage. Well, the Mirage is a hotel in Las Vegas. In science, it's caused by a non-uniform medium, meaning the optical density is not even throughout. This creates the illusion of water on the road or even in the desert. But how does this come about? You typically notice mirages on a hot sunny day because the sun heats up the roadway, which heats up the surrounding air just above it. The hotter air is less dense than the cooler air, which creates this non-uniform medium. By looking at a low angle, the light from objects appears to follow a curved path to your eyes. The light traveling downwards through the less dense hot air speeds up, which causes the light to change direction. This creates the illusion of water and produces a mirror image of objects close to the ground. Now to my favorite part of this program, rainbows. What makes rainbows so special? Well, it's not because they have a pot of gold on the end of it. We all know rainbows are formed when it is raining out, when it is sunny. It's not as simple as that. When you spot a rainbow, the sun must be behind you and the rain must be in front. That is why rainbows occur in the morning when the sun is still rising, or in the late afternoon when the sun is starting to set. Isn't that true, Mr. Bigglesworth? Rainbows are so spectacular because each raindrop acts as a tiny prism. Like a prism, the asymmetrical sides of a raindrop create refraction at different boundaries, making the sunlight disperse into a spectrum of different colors. When light travels through the water droplet, its speed must decrease, thus forming a bending of light towards the normal. Internal reflection occurs within the raindrop, which leads to a change of direction for the light. The light then escapes the droplet and the speed increases again, which bends the light away from the normal. Each tiny raindrop does a significant thing. And when thousands upon thousands of raindrops are together, it magnifies the spectacular sight. Knowing this, we can now ask why rainbows are curved. Actually, rainbows are complete circles, no corner. But from the ground, we see them as semicircles because the horizon limits what people can see on the ground. If you ever see a rainbow from a plane, you can see that it is a complete circle, and it is one amazing sight. Another reason why rainbows are so phenomenal is because red always appears at the top and follows the pattern red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv. This occurs because red refracts for the most, so when looking at higher angles from the ground, red is always at the top. Well, that's all the time we have on Fun with Science. I am Star Scientist Bob, and so long.